Okay, so 5.5 is going to be about solving the exponential and logarithmic equations. So we talked about their graphs, how to graph them, and some of their properties, especially with the logarithmic expressions and functions. And now we're going to be talking about how to solve equations that have exponential expressions in them or logarithmic expressions in them. We're going to start with the exponential equations first, though. So here are two examples of what exponential equations can look like. So it's any equation that has a variable in the exponent. And so our goal to solve these equations is to get that variable out of the exponent and then solve for the variable, get the variable by itself. So we have two properties that we can use to do this. So the first one is called the base exponent property. So what this says is that if I can get the bases to be the same on each side of the equal sign, then, like for example, this has a to the x power, I want to use smaller, a to the x power is equal to a to the y power. Well, if those two bases are the same, well then obviously those exponents need to be equal. And for this to be equal, right? So I can just kind of cancel the bases and set the exponents equal to each other. Because if I had 3, for example, if I had 3 to the 2x minus 7 power is equal to 3 to the power of 5, well, of course, for this to be true, 2x minus 7 has to equal 5. They have to have the same exponent on 3 for that to equal. That makes sense? And then I could just go from here and solve this equation for x to figure out what the solution to that original equation is. Now, so that's kind of what this property means. It's if you can get the bases to be the same on each side, then you can kind of just cancel the bases and set the exponents equal to each other and then solve from there. So you would add 7 to both sides and then divide by 2. And we're going to do some examples. But now you can only use this property if the exponential expressions are, isolated on each side. And you can only use this property if you can get their bases to be the same. So, for example of how you would use this, because it's not just going to automatically usually be already the same for you. You have to kind of think a little bit and see if you can get them to be the same. But for example, this example up here, 2 to the 5x power is equal to 64. I can write 64 as a power of 2. 64 is equal to 2 to the 6th power. So I can rewrite that as 2 to the 5x is equal to 2 to the 6th power. And then I can cancel those bases of 2 and set the 5x equal to 6. So x would be equal to 6 over 5 once I divided both sides by 5. And that would be the solution to that equation. Does that make sense? So that is the first property. The second property is called the property of logarithmic equality. So for this one, also I do want to say that these properties work going both ways. So for example, and you'll do this if you go on to higher math courses. If I had like well, I'll just make up an example. If I had 5x equal to e, I don't know. I can actually, so that would be this side. I can actually put both of those up into an exponent of a base that's the same. Like I could just write this as 2 to the 5x power equals 2 to the e power. Then that would also be true. But usually when you use it that way, when you get into higher math, it'll be used like this. You'll have like ln of something, I'll just do ln of x is equal to, I don't know, 3x minus 1 or something. And then you can raise both sides, or you can, never know how to say that. But I always called it like take the e of both sides. But you just make e the base of both sides, and those become the exponents, and then these ln and e would cancel. So that's how it's used backwards. But we're not going to be using it backwards in this class. But you will if you go on to pre-calculus and calculus. So anyways, I just wanted to make that statement. All right. So number 2. Number 2 can also be used backwards in either way, going from the log form to this form, or going backwards, and we're going to use both. So let me explain what this property means. This means that if I have log base a of m equal to log base a of n, so I have a log expression on both sides of the equal sign and they both have the same base a, well then I can just cancel the log base a and m would be just equal to n. So we're actually going to use this property whenever we're solving the logarithmic equations. So for example, if I had log base 3 of x equal to log base 3 of 2x minus 1, well, these bases are the same, so I can just cancel them and set the expressions inside equal to each other. So x equals 2x minus 1. So very similar to the other property, except for we're canceling the whole log base a. Whatever the base is, that's the same. Okay, but going the other way, this is what we're going to use first for exponential equations. So going the other way, if I have like 3x equal to the equal to 40, well then I can take the log or ln of both sides of this equation and it'll still be equal. And that's going to be helpful to us because it'll allow me to get the exponent, the variable, out of the exponent. So anyways, if I had an example like this, then technically this would be my m here, and this would be my n. And then this would be the same thing as log of 3x equal to log of 40. So I can take, this is called taking the log of both sides. Because then I know that there is that power rule for logs, which allows me to take that exponent of x and pull it out front, right? So that's why I would want to do that. Because now that becomes x times log of 3 equals log of 40. And what I can do after that, just rewriting it here, because log of 3, and notice I used log base 10, because I didn't have a base written there, because that's a one that we can easily put into our calculator. So when you use this property, you will always just use log base 10 or ln. You can use either one of those because that's the one that we can easily put into our calculator. Technically, you can use any of the other ones, but there's really no reason to use any other base except for 10 or e. So anyways, log of 3, that's just a number. If I plugged in log of 3 in my calculator, it would be equal to a decimal. And so is log of 40. So I can get that variable by itself now just by dividing by that log of 3. Because log of 3 divided by log of 3 cancels. It's the same thing. Anytime you divide something by itself, it cancels. And that leaves me with just x equal to log of 40 divided by log of 3. And then I could type this whole thing in my calculator and get a decimal. Okay, and we're going to do a bunch of examples. So, Madeline, do you want me to print out that 5.5?
That's okay.
Good.
I got a picture of it.
Okay. All right, so first example is 2 to the 3x minus 7 power equals 32. Also, I do want to just mention that you will, if you use either one of these properties, let me say this. This property number 1 can only be used if we get the bases the same. So we use this property if it's possible to get the bases the same. But it won't always be possible. So if it's not possible, then I have to use property 2. And property 2 will always work. I could literally use property 2 on any of these exponential equations, and it'll work. But the first one's kind of just a little bit easier, shortcut, if I can get the bases to be the same. Then I can just cancel them and set the exponents equal to each other. But sometimes I won't be able to get the bases the same. And then the other thing I wanted to say about this, no matter which property you use, you always need to isolate at least one exponential expression on one side. Of the equation. So sometimes you might need to divide both sides by number to get the exponential expression by itself first, and then you can use one of these properties. For example, this one here, the exponential expression is e raised to the 0.08t power. That's my exponential expression, so I need to get rid of that 100 first by dividing both sides by 100. And then I can use one of my properties. Okay, so you can only use these properties once you get the exponential expression by itself first. And it's okay if you have 2 by itself, like this one. That's fine. You have at least one by itself on one side. So if you have 2, this one's that 4 to the x plus 3, that is an its own exponential expression, isolated on one side, because there's nothing being multiplied in front of it or added in front of it. And then this one is isolated on the right side. That's fine. I can use the property on that one, and we're good. But because they're both isolated. Okay. All right, so anyways, back to number 1. Okay, so number 1, I can actually get these to have the bases be the same because 32 can be written as a power of 2. So if you don't know that, if you don't like have all your, powers memorized, I don't blame you, then you can just try by taking 2, because that's the smaller base in this problem, and just start raising it to different exponents. It's never going to be like a really large exponent. So, just try up to like 10 and see if any of those equals 32. And it will be 2 to the 5th power is equal to 32. So I rewrite this as 2 to the 3x minus 7 equals 2 to the 5th power. And now I have gotten the bases to be the same, so I can use property 1 and just cancel the bases of 2 and set the exponents equal to each other. So from here, I would just solve this linear equation. I would add 7 to both sides. Okay. And then divide both sides by 3. So x will be equal to 4. And if you plug that back in and checked, it'd be equal. 4 times 3 here is 12. 12 minus 7 is 5. So that'd be 2 to the 5th power, which is 32. For these, it's not mandatory that you check them. It's just a tool that you can use to check your work. But there's no restrictions on these type of equations. But when we get to logs, there will be restrictions on logarithmic equations, and we will have to check our answer. So that's one of those mandatory types of equations that you have to check. All right, number 2 is 3 to the x power equals 20. So for this one, there's no way that I can get the bases to match here. There's no power of 3 that will equal 20. So for number 2, I'm going to have to use the second property. Now, I already have an exponential expression by itself on one side, so I'm good there. I don't need to worry about that. And so for step 1 of this problem, I'm going to take the log of both sides. That's just how we say it. Take the log of both sides. You could also take the ln. It doesn't matter. You'd get the same answer. I'm going to do one with the ln. But I'm just going to use log for this one. And so that would be log of 3x is equal to log of 20. It doesn't mean log times 20. It's log of 20. The 20 is inside the log function. So this one's very similar to that other example I did up here. I just changed 40 or 20 to 40. So after you take the log of both sides, you will use the power rule. So step 2, use the power rule of logarithms to get the exponent of x, or sorry, let me say it like this, to get the variable out of the exponent, because that's always our goal. I don't know how to solve an equation with a variable in the exponent, except for by doing this. I have to get it out of the exponent. So that x, which is the exponent, will come out front and multiply by the log of 3. And then from here, I will solve for x by dividing both sides by log of 3. Because again, that's just a number. But you just don't want to write it as its decimal until the very end, because you'd be, for one, you don't want to round until the very end, or you could get it wrong. Because in math, we just don't like to round until the very end, because that could really, it could change depending on how people round their answers, right? So at the very end, you will round. So just keep everything in terms of logs. But this will cancel. And this will be equal to log 20 over log of 3. Okay. Now, sometimes they might ask you for an exact answer. And if they ask for an exact answer, you would literally enter this into Pearson. Just keep it like that. But if they want you to round it, then you type this in your calculator. And you need to make sure that when you type this in your calculator that you close the parentheses. So let me see. Why does it do that? Sometimes it works and sometimes it doesn't. See if I go back. Mm-hmm. Okay. Well, just bear with me. Okay, so we are typing in log of 20 was on top, right?
Yes.
And then close those parentheses. And then hit the divided button, because that's the same thing as fraction. And then log of 3 and close your parentheses. And hit enter. If you don't close the parentheses after 20, then it'll think that you're putting another log, like 20 divided by log 3 in that first log. So you have to tell the calculator what you're doing. That's the end of that log, and now I'm dividing by a new log. So then you hit enter, and we get this, and we'll round to the nearest tenth, which will be 2.7. They'll tell you what to round to on Pearson. Just make sure you close your parentheses after the log. So that's approximately equal to 2.7. All right. Number 3, like I said, for number 3, I need to get the exponential expression by itself first. And the exponential expression there is just the whatever the base is and the exponent of the base. So that is the exponential expression with a base e. So the first thing I'm going to do is divide both sides by that 100 to cancel it, because it's just being multiplied by the e to the 0.08 t power. So I can just divide and it'll cancel, but I need to divide it over here. So that will leave me with e to the 0.08 t is equal to 25. Okay. So I got the exponential expression by itself. Now for this one, we could take the log of both sides if I wanted to. But the easier method is to take the ln, because remember ln of x, I'll just say, is equal to log base e of x, right? ln is just the log base e. So if I take the ln of both sides here, this would be ln of e to the 0.08 t equals ln of 25. What happens? Do we remember?
Move the exponent to outside of ln e.
And what is ln of e? That's what I'm trying to get at here. It cancels. Because remember, again, ln of e would be the same thing as log base e of e, right? So anytime you take the ln of e, it's just equal to 1, really. So this is the case of like this. It would look like this. ln of e to the 0.08 t power is the same thing as log base e of e to the 0.08 t power. Remember, we learned that if we had this, that just all canceled and left me with the exponent. But also you could have seen that from using the power rule. Because if I pull that 0.08 t out, using the power rule, then it gets multiplied by ln of e, but ln of e is just 1, because ln of e is just log base e of e. And we learned that this is just equal to 1. So either way, but we already kind of learned this property. If those bases are the same, it just cancels and leaves me with the exponent. And that's how you can always think of ln of e. ln of e, it'll just cancel. It's equal to 1. So if there's an exponent on there, it'll just cancel and leave me with the exponent, 0.08 t. I guess I could have left that up there. Okay, so from here, I can just divide both sides by that 0.08. to get the t by itself. So t would be equal to ln of 25 divided by 0.08. So again, I can just type this. If they wanted an exact answer, I would just leave it just like that. But if I put this in my calculator, I'm going to type ln 25 and close my parentheses, and then divide it by 0.08. And this would be approximately equal to 40.2 if I rounded it to the nearest tenth. 40.2, yep. Okay. All right. Number 4 is pretty long. So I'm going to write it on a separate piece of paper because it takes a lot of steps to solve number 4. What is it? 4 to the x plus 3 equals 3 to the negative x?
Yes.
Okay. All right. So anytime you have 2 exponential expressions on both sides with variables and the exponent, it's pretty tedious. It's kind of a long problem. But I'm going to give you the steps. The steps will always be the same. So I'm going to write these steps out. So step 1, we already have at least one of these isolated on one side. So that's good. And honestly, that's how it will be in any of the problems you see. You won't really have one that's like 5 times 4 to the x plus 3 equals 3 to the negative x. You won't have anything like this, so just don't worry about that. It'll be like this. So step 1, we are going to take the ln or the log. Doesn't really matter which one you use. I will take the log. So that will give me log of 4 to the x plus 3 power equals log of 3 to the negative x power. So all of that is inside of those 2 logs now. And then step 2, we will use the power rule. To pull the exponents out front, to pull the exponents out front. Is that a good way to say that? Use the power rule to rewrite these as a product. So the exponent in the first log is that entire x plus 3. All of that was up in the exponent. So when I go to use the power rule there, I need to put all of that in parentheses because that entire exponent needs to be multiplied by what's left, which is log of 4. So if it's more than one term in the exponent, you need to put it in parentheses because we're going to have to distribute there. Equal, and then the other exponent is negative x. So that negative x will come out front and be multiplied by log of 3. So step 3, like I said, this will become a distributive property. Log of 4, again, is just a number. If you typed it in your calculator, you would get a decimal. So it's just some number times x plus 3. So I'm going to distribute log of 4 to both of those terms. And get x times log of 4 plus 3 times log of 4 equals negative x log of 3. All right. So from here, this is where students usually forget what to do. But if you can just, I keep saying it, if you just remember that any log of a number is just a number. So that's a number being times a variable, right? So that's the coefficient of that variable. I could write it in front if I wanted to. This whole thing is a constant term, because that's all numbers, 3 log of 4. So that would just be some decimal. Let me rewrite this too. This would be a variable term because it has a variable in it, the x. And this is a variable term because it has a x. So we're going to treat this just like it was a linear equation to solve for x. I have 2 x's here, so I need to get all the variable terms to one side and all the constant terms to the opposite side. So I'm going to rewrite. I'll just rewrite the problem first to show you what I'm doing. So what I'm going to do is I'm going to add x log of 3 so that those 2 terms cancel. But then I have to add it over here at plus x log of 3. So that will cancel here. And then I'm going to subtract the constant term to both sides so that that'll cancel there, and I'll move it to the right. Kind of did 2 steps in one there. So what this will leave me with, I would have, you don't want to like try to combine these like terms, even though technically they are like terms. We're not going to try and combine them like terms. I'm just, because I don't know what log of 4 is or log of 3 is yet. I could figure it out in my calculator and get a decimal, but I don't want to write them in their decimal form until the very end. So I'm just going to rewrite that as x log of 4 plus x log of 3 is equal to negative 3 log of 4. So this is the one that I added to the left, and this is the one I subtracted to the right. So that's what that left me with. I know. Okay. Step 5. Okay, so remember what my goal is. My goal is to get x completely by itself. Well, now both of these terms here have an x in them, a common factor. So I'm going to factor the x out. The GCF of x. So that would be x times log of 4 plus log of 3. That's what that would leave me with. Equals negative 3 log of 4. And I should say factor out the GCF of x and then solve for x, because now we can just solve for x. Because now I have x times all of this, but all of this is just a number. So I can just divide by all of that to both sides. To cancel it. Anything divided by itself will cancel. So this will leave me with x is equal to negative 3 log of 4 divided by log of 4 plus log of 3. And that would be the exact answer. And so let's type this in. Any questions about how I got, any questions about all that? No, it's a lot. It just looks more complicated because there's logs in there. But if you just kind of remember that that log of a number is just a number, then you just treat them like constants after you use the power rule, whatever. All right, so let me see if it'll work this time. I don't understand why it works and sometimes it doesn't. That's fine. Okay, but I am trying to do this on 2 screens. So I know, first of all, to keep my life easier, if you have a TI-84, you can hit that alpha fraction button to get you into fraction mode. That'll make your life so much easier. If not, you have to put everything in the numerator in parentheses and everything in the denominator in parentheses. So if you don't have this feature, let me know and I'll, walk you through how to do it the other way. But the top was negative 3 times log 4. And then we want to close our parentheses. And then hit the down arrow to go down to the bottom. And then, since we have this fraction feature, it's not that important. I don't have to put all this in parentheses. But if you didn't, you'd have to put it all in parentheses. So this was log, what was the first one?
Log of 4.
Log of 4.
Plus log of 3.
And then make sure we close that parentheses so it knows that's the end of that log, plus log 3. Okay. Hit enter. And it gives me negative 1.67 if I rounded to the nearest hundredth place. So let's round it to the nearest hundredth place. 67. All right. So that will always be the process if you have two exponential expressions on each side. You'll take the log or ln of both sides, use the power rule to pull the exponents out front. If one of those exponents has more than one term, you need to distribute that log to both of those terms. Then move all your variable terms to one side and all your constant terms to the opposite side. And then once you do that, you'll be able to factor out that common factor of x. And then just divide by what's left to both sides. All right. Moving on. So now let's talk about solving logarithmic equations, which, in my opinion, I think is a little easier than the exponential. Well, except that you have to, these logs have restrictions. Do we remember what the restriction is of a log? Or what's the domain? What can x not be? Negative or? 0. X has to be greater than 0 in a log or an ln. That's always true. Well, I should say the expression inside the log. So I just wrote x here, which means that that's the only thing in that log. So that x has to be greater than 0. And if you type in log of any negative number in your calculator, it'll give you an error. You can't do it. You can't type in log of 0. It'll give you an error. It's just not in the domain. So that is something we need to be aware of when solving these equations. This is one of those types of equations where it's mandatory to check your answers, because sometimes when you do all the work and you get to the solution, some of those solutions will not be solutions because they make your original equation undefined because of the domain of logs or the restriction on logs. Okay, but we're going to talk about that. So here are two examples of logarithmic equations. So of course these are just equations that have log expressions in them. And I have the steps here written on how to solve them. So we really don't need to learn any new properties. We've already learned all the properties that we need to know to solve these, actually. One of the main properties we're going to use is going from logarithmic form to exponential form. That's going to be very helpful in solving these. And then the other property that we're going to use is the one we just learned about, this one here, but now we'll be going backwards. So if I have two logs equal to each other on each side of the equation, I can cancel the logs and just set what's inside the logs equal to each other. So we could also use that property. All right. So step 1 says to rewrite each side of the equation as a single logarithmic expression using the properties of logs. So if I have something like this example here that has two log expressions on the left and they're being added, so I could combine those into one single log using, do we remember what property? If they're being added. The product rule. Remember this?
Oh,
So if they're being added, then I can combine them into one where they are now being multiplied. The expressions inside the two logs. So that's how we're going to do step one if we need to. We're going to use those properties we learned, the product rule, the quotient rule, or the power rule, to rewrite them as one single expression. So going further on number 2 here, this would become log of x. Well, yeah, I guess I could do this. That's fine. Log of x times x plus 3. Because that was my expression inside the first log, and this was my expression inside the second log. So now those two expressions get multiplied by each other, but I have to put the x plus 3 in parentheses because it's two terms. And so then I can distribute that x and get log of x squared plus 3x equals 1. Okay. So step 1, I used the product rule there to combine them into 1. And then I just distributed the x. Now let me go back up here to the steps. Oop. Oh my gosh. So step 2. My iPad is really getting on my nerves. So step 2, if there is only one logarithmic expression on one side of the equation, then we will rewrite the equation in its exponential equation form and then solve for x. So that's what I have in this case. Now, this is just one single log expression on the left, and it's equal to some number on the right. So I can rewrite this in its exponential form using this up here. I can go from its logarithmic form to its exponential form using that rule that we learned. So what is the base of this log? 10, because it's not written there. Anytime it's not written, it's understood to be 10, because that's our most common number, right? So if you don't see a base, it's 10. So to write this in its exponential form, I need to start with the base of 10, and it gets raised to the power of 1, and then that should be equal to what's inside, which is x squared plus 3x. So there we just rewrite in its exponential form. Exponential. And what kind of equation is this? What kind of equation is this?
Binomial? Or quadratic?
Quadratic. This is a quadratic equation because the highest exponent is 2. Okay, so you will have some problems on your final for sure about solving quadratic equations, just solving quadratic equations in general. So let's make sure we remember how to do that. The first step is I need to get that equal to 0. So I'm going to subtract the 10 to both sides. Oh my gosh. Okay. And so this would be x squared plus 3x minus 10 equals 0. And then I factor this quadratic. So I need two numbers that multiply to give me negative 10 and add to give me 3. Negative 2 and positive 5. Okay, so I see a lot of students, they get this far, well, maybe not on the log brush, I'm just kidding. You guys will be just fine. But even with the quadratic equations, they get this far and they just think that's the answer. Negative 2 and 5 is the answer, but it's not. That's the numbers you use to factor it. Now I need to set each factor equal to 0. I'm running out of room. So x minus 2 equals 0, or x plus 5 equals 0. And then solve these. So I would add 2, so x would be equal to 2, or x would be equal to negative 5. And then these are just possible solutions. You have to plug them back in and check them now. So I'm sorry if you're running out of room on your notes. I keep moving stuff. So now I need to check these. Now remember, and when you check them, you have to plug them into the original equation. Don't try to plug them into this one, because it could be misleading. So my original equation is log of x plus log of x plus 3. So which one of these do you think is automatically going to be eliminated? Negative 5. So x cannot equal negative 5 because that first one, log of negative 5, is undefined. I don't even care about the other one, even though it's also undefined. This one here, if I plug negative 5 in for that x, log of negative 5 is undefined. So that is not a solution. Error.
No.
What do you mean?
Sorry.
Oh, okay. And then for 2, dang, how did I write this on the last one? I'm running out of room. For x equals 2, I would have log of 2 plus log of 2 plus 3 equals 1. Now, so I just plugged 2 in for those x's in the original. You could literally plug this whole left side into your calculator and see if it equals 1. Is that what you just did? Yeah. And it'll equal 1. Or you could go through the motions, log of 2 plus log of 5, and then combine these using the product rule, which would be 2 times 5, which is 10. And log of 10 is 1 because it's log base 10 of 10, and that is equal to 1. So that checks. So the only solution to this problem is x equals 2.
This is so crazy. This feels like a trick.
Magic. I probably should have started with the easier one, but whatever. We're here. All right. Now, number 1, which is an easier one. Oh, and then by the way, so we did step 1, we did step 2, and we did step 3. Because we checked our answers to make sure that nothing made the inside of the original logs negative and that it was true. So we did that. The only thing I haven't talked about yet is this one, but we will, because we just haven't had that case yet. But we will in number 3. So let's just go over number 1 real quick. So number 1 already has the log expression by itself. So I can just go straight to transforming this into its exponential form. So that will be my step 1. Or rewrite, transform to its exponential form. So in this case, my base is 3, so that's where I start with. And then it gets raised to the power of -2, and it's equal to x. So this one was just, well, technically it's, what do I want to say? Really, this is the answer, 3 to the -2 power. I already got x by itself, so that was super easy. But, I can't write this answer with a negative exponent. So now I just have to rewrite it with a positive exponent using that rule. So what would this be equal to as a positive exponent?
1/2.
Hmm?
1/2. Well, the exponent would turn into 1/2.
Close.
Sorry,
You're okay. So if I remember, I got to put this over 1 and then flip it. Closer. Be 1/3 to the +2 exponent. Well, what is 3 squared?
9.
9. So that comes from that exponent rule. If I have anything to the negative exponent, this is equal to 1/x, and then you make the exponent positive. So just put this over 1, flip it, and make the exponent positive. So we've talked about this.
So 1/9 is the answer?
Yep. 1/9 is the answer.
And there's no way to really do that with the calculator, huh? You just gotta know how to do that.
Yeah.
Yeah.
Let's see. Well, there is a way. Let me show you. You can do it like this. Ready? You can type in 3, raise it to the -2 power, hit enter. It gives you a decimal, but then math fraction it. Enter, and it gives you one. But if you
What is wrong with me?
But if you plan on taking higher maths, you need to understand this rule, okay? You
Yes.
need to know how to write this as a positive exponent. Because when you get to higher math, it'll be variables, and you won't be able to type that in your calculator. Okay, but yes, I'll do it one more time. Let me do it on my screen too, so the people at home can see what I'm doing. So we're trying to rewrite 3 to the negative 2 power as a fraction. So you type in 3, the up arrow to get the negative. Oops, that's not what I meant to do. 3 up arrow negative 2. Make sure you use that negative symbol down there, not that one. Hit enter to get a fraction, or a decimal, sorry, thank you. And then hit the math button, and it's on fraction there, and you just hit enter, so it'll turn that decimal into a fraction. It'll bring you to that screen. Just hit enter one more time, and it gives you 1/9. That's how you rewrite. Well, that is the fraction equivalent to 3 to the negative 2 power without using negative exponents, which is, we don't like to write answers with negative exponents in math. We don't. So you always have to write them with a positive exponent and then simplify.
So on the test, would you want us to like figure it out, or just
You can put it in the calculator. But you should probably still know how to do it by hand, because I'm trying to think of an instance where maybe like you would, like if it was a variable or something, you know, and then you can't put it in the calculator. So yeah, try to understand, but you can lean on that to check your work. All right, number 3. So remember the steps again. So step 1 for these, we're going to rewrite each side of the equation as a single, logarithmic expression using the properties of logs. So for number 3, I need to rewrite this left side as one single ln expression. So they are being subtracted. So what rule would that be to combine them into one? The division. And that's called the quotient rule. You're okay. But same thing, is definitely using division. So this would be ln of the first one, 4x plus 6, divided by x plus 5. So that's combining it into one ln expression using division. And then this would be equal to the ln of x over there. Okay, so this brings me to the second case up here that I had starred. Because for step 2, it says if there's only one logarithmic expression on one side, then you can rewrite it in its exponential form like we did with 1 and 2. But if there is one logarithmic expression on each side of the equation, like we have here at number 3, then I can use that property of the logarithmic equality and just cancel the logs or the ln's and set what's inside equal to each other. Okay, so that's that property we learned right here. If I have 2 logs equal to each other, I can cancel the logs as if they have the same base and set what's inside of them equal to each other. So I can do that here. These ln's will cancel, and that will leave me with 4x plus 6 over x plus 5 is equal to x. So you can only do that once you have like 2 logs or ln's equal to each other on each side and nothing else on the outside of them. Okay, and then this is a rational equation. So do we remember how to solve this?
You do the opposite backwards thing. I forget what it's called. It's a C word.
Not for this one, right? Then I know what you're talking about, the conjugate.
Oh, yeah.
That's for like i's, imaginary numbers, or radicals. But this is just, this is an equation that has a fraction. So I want to clear the fraction. How do we clear fractions?
Multiply by itself.
Close.
Multiply the denominator on both sides.
Multiply by the denominator. Clear the fraction by multiplying each side by the denominator. Denominator? Because that's how we clear fractions. If I multiplied the left by x plus 5, it will cancel, which is what I want to get rid of the fraction. That looks nasty. Don't like fractions, so let's just get rid of it by multiplying by that denominator. But I need to multiply by the x plus 5 on both sides. So these will cancel, and that will leave me with 4x plus 6 is equal. Then I need to distribute that x on the right, so x squared plus 5x. And now this is another quadratic equation. So we're getting some practice with the quadratic equations here, which you will definitely have on your exam. And I know it's quadratic because it has an x squared. And the first step in solving a quadratic equation is to get it equal to 0. So I'm going to subtract 4x to both sides, so it'll cancel on the left, and I'll subtract 6 on both sides, so it'll cancel on the left. And so that will leave me with 0 is equal to x squared. 5x minus 4x is 1x, so that'd be just plus x, and then minus 6. And then we will factor. So I need two numbers that multiply to give me -6 and add to give me a +1. So that would be -2 and +3. Right. Now that I have it in its factored form, I'll set each of these factors equal to 0. So x minus 2 is equal to 0, or x plus 3 is equal to 0. So I get that x is equal to 2, or x is equal to -3. But again, these are my possible solutions. And so I need to check them. So remember, you always need to check them in the original equation up here. Do not try to plug them in anywhere else. Because if they make any of those ln's negative, then it's not possible. It's undefined. So which one will make it definitely negative? -3, because of this ln of x here, for sure. If I plug in -3 for x there, that's ln of -3. That is undefined. Bad. So x cannot equal -3, so this will not be part of your answer. If you put -3 in there, you'll get it wrong. Because ln of -3 is undefined. then I will even highlight that, where I'm plugging that in and getting that from. Okay, but 2, be ln of 4 times 2. 4 times 2 plus 6 minus ln of 2 plus 5 equals ln of 2. Now again, you could just plug all this left side in your calculator like that, see what that's equal to, and see if it's equal to ln of 2, and if it's the same decimal, then we're good. 2 is not going to make any of these negatives, so we're also good. But this will simplify. 4 times 2 is 8. 8 plus 14, or 8 plus 6 is 14. 2 plus 5 is 7. And then I can combine this into one single log, which would be ln of 14 divided by 7, because of the minus, and that is the quotient rule. 14 divided by 7 is 2. So this is equal to each other. So x equals 2 is the only solution. And that would be the answer. Okay, I'm just going to finish 4 and we're going to take a break. Number 4, what's my base? 10. So, and the log's already by itself. Are we good? Did y'all copy all that down? Okay. So, how do I rewrite this? 10 to the negative 3 power equals x. Perfect. 10 to the negative 3 equals x. Okay, and then I need to rewrite this because it's a negative exponent. So I can put it over 1, flip it, and once I flip it, the 3 becomes positive. And then 10 cubed is 1,000. So 1 over 1,000 is the answer. It's not that hard.
No, I think you started with the hardest one, made everything
I know.
smooth.
But I mean, this rule is not that hard.
Yeah, the first one was
Okay, break. Let's take a break.